Hi, this is Mr. Royks, and this lecture is going to be on electrons. And so this is sort of a recap of what we have already discussed in class. But for those of you that missed it, this will be new material, and you might want to take some notes, anything that you don't already have down. So when we talk about electrons, electrons are the driving force behind chemical reactions. So everything that occurs that is a chemical reaction is based on electrons, and basically the atoms trying to get to a more stable more stable level of energy, and that energy is based on the number of electrons they have. So if we think about the earlier models of the atom that we've talked about in class, whether it be J.J. Thomson's plum pudding model, where the electrons are just scattered about, or the idea of Rutherford, where the electrons are outside of the nucleus, and then Niels Bohr, the model of the atom that we're most familiar with. And here's my poorly drawn model of Bohr's atoms. But most importantly, what I want you to realize is what Bohr did understand about the atom, and what he was right about was not the fact that electrons follow fixed orbits, but there were energy levels that electrons have. And so you can see in my crude drawing that, again, there's certain distances from the nuclei which basically represent energy levels. Although the other thing, they're often referred to as shells. So energy levels are shells. So there are distinct energy levels or shells that each electron have. Now, in the past, in science classes, you may have talked about the number of electrons allowed in each shell, and very likely you had something, or you came across something called the 2882 rule or something like that. And so what that did is it gave you kind of the basis for the energy levels for the first 20 elements. And so you may have drawn out some atomic some electron shells. So here's a quick representation of hydrogen, lithium, and sodium. And so if you again follow the 2882 rule, hydrogen has only one electron, so you put it in that first shell. There's one electron. Lithium has 3 electrons, so you'd put 2 in the first shell. And then the last one would be here. And then you look at sodium, and as you can see, sodium has a total of 11 electrons, so 2 in the first, 8 in the second shell, and then the last electron located right here in the third shell. And again, so what I was saying is, in the past you follow that 288 rule. That gets you up to the first 20 elements. And then it gets a little bit different. We'll deal with that a little bit more. But most importantly, what I want you to recognize is for each of these elements, they have what we call an outermost electron. Okay, so hydrogen has one, lithium has one, and sodium has one. And those outermost electrons are called valence electrons. So as I was saying, electrons are the driving force. Technically speaking, it's the valence electrons that are really the driving force behind reactions. And so one of the things that if you again go back to this 2882 rule, is there's a maximum of 2 electrons in that first energy level. So hydrogen is really just 1 electron short of having a full, what we call a full outer shell. Lithium, right, is 7 electrons away from having a full outer shell, right? Or it is just this one, getting rid of this 1 electron would get it to a full outer shell, because the inner shell would be full. And so sodium, again, is the same way. So what I described in class is, say we have a single book on a desk. So there's our single book, this is our desk. And I told you that we'd like to group the books, and we'd like to group them in groups of 8. So here we have a single book, right? Here we have a stack of 7 books. So energy-wise, does it make sense for sodium to try to grab and bring to it the stack of 11 books, or 11 electrons? Or would it make more sense for sodium to just give up this one electron, and then if you look, if sodium were to lose this one electron, it would then revert to this inner shell with 8 full electrons. So the idea of having 8 electrons in the outer shell, or the valence shell, is called the octet rule. So having an octet of electrons. Now there are some exceptions to the octet rule. The one that you guys will experience probably the most is what we have over here with hydrogen and lithium, some of the lighter elements, where if we go back to the first shell only needing 2 electrons, or only having 2 electrons, then it has a full outer shell. Hydrogen can sometimes gain 1 electron, but more likely hydrogen will just lose both of its electrons in general. And so if you notice that hydrogen, lithium, sodium are all found in this first column of the periodic table, okay, all of them have, or all of those elements have 1 valence electron. And so all of these elements will lose 1 valence electron to get to that octet of electrons, or again, with the exception of hydrogen and lithium, get to that complete outer shell, that inner shell having only 2 electrons. So those are valence electrons. What you also may be familiar with, or what you may have done in class previously, is done the dot diagrams. So the next thing I wanted to mention was the electron dot diagram, or the Lewis dot structure. Again, something that I think you guys have done in the past, and that is basically where you have an elemental symbol and you use dots to represent their valence electrons. So hydrogen would have 1 dot, lithium would also have 1 dot, sodium would have 1 dot. So all of the group 1 elements would have 1 dot. If we look at the group 2 elements, we have beryllium. We would give beryllium 2 dots. We have magnesium, so magnesium. And so we have this pattern as we go across the periodic table, or with adding a valence electron. And that is true down the rows of the columns of the periodic table. The columns of the periodic table are all going to have the same number of valence electrons. So group 1 would have 1 dot. Group 2 would have 2 dots. Now again, we're going to skip this section of the transitional metals, and we'll explain those a little bit later. But group 3, boron would have 3 dots. Carbon would have 4 dots. Nitrogen would have 5. Oxygen 6. Fluorine 7. Everyone in that group would have 7. And then lastly we have the noble gases, which would have 8, with the exception of helium. Helium would just have 2 dots. So if we did helium, it would be He, and we give it 2 dots. But if we pick out one of these other ones, say fluorine, fluorine would have 7 dots, 7 valence electrons. So my only rule with valence electrons is you only put 2 per side, because electrons will pair up. So there's fluorine with 7 valence electrons. So everything in that fluorine group, chlorine, bromine, iodine, acetine, if you were to draw the dot structure, would all have 7 dots just like that. Alright, so we're going to stop there, and we'll talk a little bit more about electron configuration later. See you in class.